All right, so good afternoon, everyone. Today is day three of the DSA Bootcamp. We'll be going over hash maps today, or more of an introduction to hash maps today. Right, so a hash map, right, is a data structure that is used to store key value pairs. Right, it's also known as a hash table or a dictionary in Python, an object in JavaScript, or a map in Java, and so on. Right, each key is unique and is used to access its corresponding value. Right, so think of a hash map as a real world dictionary. Right, it's used to look up a particular key and check its corresponding value. So the main idea behind hash maps, right, is hashing. So how do hash maps how does the data structure work underneath, right? The key um functionality under it is hashing. Right, the hash function takes in the key as the input and produces an integer called a hash code or a hash value. Right, so this integer is used to determine a block in a fixed amount of space where it will be used to store the key value pairs. Right. So the hash functions, what are the properties of the hash functions? So the hash function is deterministic in the sense that for um if you hash a particular value, right, you get a particular hash, right? If you hash the same value, you get the same hash essentially, and if you hash a different value, you get a different hash. But in some cases, right, there are cases whereby you hash a value and you hash two different values, right, and you get the same hash. In a very, very rare case, but it is still possible. The hash function also helps in uniform distribution, right, in the sense that the hash function helps to distribute keys evenly across a fixed amount of space or across the defined space that we define for our hash map. Yeah, and what is the hash function is also efficient, right? It helps in computing a particular index in our or in a block of space, right, for a particular key value pair. Right, so underneath, right, the a hash map consists of some things called buckets, or like more easily, right, consists of, should I say, um like more containerized mini structures. Let me put it like that, right? So the bucket array is the underlying data structure where the key value pairs are stored. Right. So the hash code, the hash generates the hash function generates an index, right, where we can store where yeah the function, right, generates an index in a particular list where we can use to store our key value pairs. So let me explain what I mean. So let's say, oh, let's do this dots. So let's say this is our um yeah, let's say this is our dictionary, our object, right? So for the underlying architecture, we have some things called buckets. Buckets are more like I said, uh, mini, let's say mini placeholders for our key value pairs, right? So this is a buckets, this is buckets, right? So here we can have key value key. Sorry for the rough diagrams. I have key value, yeah, and so on. But we get the idea, right? So yeah, moving on. Yeah, so these buckets, right? They are kind of the ideally, right? Some buckets are connected, right? Depending on how you want to design your hash map. Yeah, depending on how you want to design your hash maps, you can have different um data structures underneath. Some hash maps, some custom implementations have, let me see if I can type here. Okay. Let's see if I can type. Yeah, so some custom implementations of hash maps, right? So let's see, this is a hash map. Some custom implementations of hash maps have lists underneath, right? That keep track of um the key value pair. So let's say this is name. Say the name is Josh. Right. So the name is Josh. Let's see age. Change this. See the name is Josh. Let's see age. Some 29. Let's see occupation. See just is a constructor. Abi, let's just see Sui. He's a software engineer. Right. Let's see hobbies. Likes to play tennis. Right. So this can be a for some implementations of hash maps, right? This can be the underlying implementations for a hash map, right? And before what we explained was the hash map, the hash function takes in the key, right? So before, if you have something like let's see, map dot insert Josh. Okay, let's say we insert Josh. This should be the key. The key should be name, and the value should be Josh. Right. So when we do this, what happens underneath is, let me see if I can move this. Okay. So what happens underneath is the hash function. There'll be a hash function to compute an index in this our in like a final array. Let's say we have a final array, more like it's the array. Right. Let's say we have a fixed space. Let's say we have a hash map of, see we have a map space. What was this? 0, 1, 2, 3, 4. Say 5. Right. And what if we do map.insert, right? What map.insert does is it computes a hash that returns the index of where we are going to store this particular key value pair. So when we do dot insert in a hash map, what it does is it calls a hash function on the key and spits out an index for us. So let's say, okay, here we know Josh is at index 0. So let's say this hash function returns 0 for us. And now we are going to store the key value name and Josh will be at index 0. I don't know if that makes, so yeah, that's what happens underneath the hash map, basically. Yeah, there's a possibility of a collision, right? So what is a collision? A collision occurs when two different keys produce the same hash code, right? Like I mentioned before, it is possible that two different keys can generate the same hash code, right? Regardless of how, should I say, mathematically complex you write your hash functions, but it is still possible, right? So let's say then the collisions are inevitable, right? Especially when the number of keys is larger than the size of the bucket array. Right. So one way to go about um, um, handling collisions, right? There are different methods of handling collisions, right? But um one method is called separate chaining. So what in separate chaining, what occurs is the buckets, right? These buckets are data structure for the buckets are called linked lists, right? So what happens is when we let's say we have two key value pairs. Let's see, let me move this guy. Let's say we have map dot insert see name Josh. When we do map dot insert, the hash function returns the hash function for name is the hash function returns 0. Then when we do map dot insert for fruits, we get let's say fruits apple, right? So let's see the hash function also returns 0, right, for fruits. So in this case, what do we do exactly in our hash function in when we want to store these particular variables? Because it doesn't necessarily fault any of the default um, parameters or the default constraints for hash maps, because these two keys, they have two different names. Assuming they were of the same name, now we can say, oh, this key already exists, you can't impede this key. But in this case, there are two different keys and they give us the same hash code, right, when we hash them. So what do we do? A case where that happens is I mentioned the buckets array, right? So instead of using an array, we can use a linked list, right? Where we have, so let's say we stored Josh initially, right? So we know Josh is here. But in a linked list, we have a next pointer, right? Essentially what it means is that there's a um there's a relationship to should I say a next node, right? So essentially, a link what a linked list is a data structure that comprises of a value and a pointer to the next node or the next list. So this is a linked list. We can have this, this, right? So this guy prints this guy, prints this guy. So of key. Yeah, we can have the key value here. Yeah, the key. So one way to avoid this situation is we can have the underlying bucket be made up of linked lists, right? So in the linked list, well, a one node will contain the key, the value, and then a pointer pointing to potentially another node or a null value. Then in the case where we have in the case where we have a collision where two keys return the same hash code or the same index, right? What we can do now is have the pointer of this initial key at that particular index point to another key, right? That give us the same hash index. So in this case, we'll have this now. fruits and okay, not just fruits and apple, right? So this is valid. This is a valid linked list. That's a valid link. It's a valid dictionary because in this particular index, right, we have two different keys, right, that potentially give us the same hash code or the same index, right? So this is one way of handling collisions where we have the buckets themselves be linked list. Then anytime we have a collision, the last value in that particular index, we just have it point to the newly computed key value. So yeah, there's another way. So there's another approach called open addressing, right? In the case whereby when a collision occurs, an algorithm scans the remaining spaces present in the list to hold the key values and determines the determines as it kind of determines the next place to um drop the key value pairs, right? So in a case whereby okay, yeah, this okay, let's say we have an empty array. Okay, can I copy this? Sure, it's okay, it's cool. Yeah, let's say we have this. Yeah, can we delete? So let's say we have empty slots here. So you have empty slots here, and we want to add key value pair fruits and apple. So let's add fruits and apple. Right. So in open addressing, we can have our algorithm check the let's say the remaining slots, right? Let's say we can have our algorithm check the remaining slots and say, oh, okay, let's say the next best place to add fruits and apples is at index 0, 1, 2, 3, 4, at index 4. Right, that's another way to kind of address collisions as well. So for that, that's called linear probing. Then there's another type of open addressing system called quadratic probing, right, where it checks the slots at increasing quadratic offsets. And there's the last type of probing technique called double hashing, which uses a secondary hash function to determine the next probe sequence. So okay, um, so this shouldn't be. This should be. So this should be dictation of hash maps. Okay, so let's look at the time complexity for hash maps, right? So with a good hash function and effective collision handling, hash maps offers O of one average time complexity, right? That's constant time for insertion, deletion, and retrieval, right? Why or how can we prove that it offers O of one? Right, so let's say we have a hash map. Let me use this again. Right, so let's say we have a regular hash map now. So, Josh. See age. Let's see 29. See occupation. See. Tennis. Okay. So let's say this is our map. Right. So it says um so the hash map offers constant time, an average of the constant time complexity for insertion, deletion, and retrieval operations. Right. So why is that? So let's say we want to get the value just now. What we just do is do map the get and the key. What is the key? Which is name, right? So under the hood, what this does is the hash map will compute the index for this particular key, which is our index 0, right? Computes the index, which is our index 0. It says, oh, okay, this is a key, this is a valid key at index 0, and it just returns this particular stuff. It doesn't need to necessarily scan through everything. It doesn't need to do a for loop. What it just does is it gets the key, computes the hash code, which also gives the index. Start computing the index. What do? We get the particular value at that particular um point, at that particular index in our hash map, which is effectively an O of 1 operation. So the next is for deletions, right? Oh, that was for retrieval. Next is for deletion. So for deletion, what we want to do is just get, still like when we do a map dot delete, let's say we want to delete the age from this hash map. So what it does still is compute the the hash function computes the hash code or the index, and then at that point, or at that particular um block in the array, right, at that particular index, it can just replace it with none instead of having this key value pair, and that's all. That's deleted it. And next time you want to get it, you will have an error because that particular key doesn't exist when it computes the index for it. To compute the index to go there and say, oh, there's no value there, everything is none, and it's just return an error for you, which is effectively an O of 1. It doesn't have to scan through the whole elements in the hash map. Same thing for insertion as well. I think insertion is pretty easy. If you want to add a new key, what we just do is we can do map to add. This is not a valid, I'm not sure it's a valid Python operation, but pseudocode. So this is, let's say we want to add the salary, right? Salary is 20k. So what it does is it scans through the hash map, right? Or what it does is first it to compute the index for this particular key, salary. Right? After computing the index, what it does is it checks, oh, in this my hash map that I already have, let's first check if the index is within bounds, right? If the index is not within bounds, it's a resize, then so then subsequently add the key and value. But if the index is within bounds, it checks, okay, if the index is within bounds, is anything there? If anything is not there, or if the value at that particular point is none, it will go ahead and add it, right? But in case of a collision, right, and we are using a linked list bucket array, what we just do is we iterate through the linked list, right? So we iterate through the linked list, and when we get to the end of the linked list, we add it. So best case scenario is O of 1 when nothing is there, nothing is at that particular index, and we just insert it, right? But worst case scenario is, let's say something is there and there is a long, like our dictionary is very, very long, and unfortunately for us, there have been collisions up and down. We have, let's say, particular five collisions in one particular index, and now we are adding salary again. So when we compute that index, you still need to iterate through all the buckets in that particular index and get to the end, then add this new key value pair there. So that's why you see in worst case scenarios, many collisions leading to long linked lists and separate chaining or poorly distributed hash functions, the performance can degrade to O of n. And we also have the load factor, where the load factor is the number of entries divided by the size of the bucket array, which affects performance. Says the high load factor increases the likelihood of collisions, but hash maps often resize the underlying array when the load factor exceeds a certain threshold to maintain efficiency. So the last part is the real applications of hash maps, right? So the real world applications for hash maps, we have caching, which is a very, very common use case, right? Caching is used to store frequently accessed data for quick retrievals. If you've, if I don't know if you've not heard of caching, okay, but caching essentially involves, like it says, storing frequently used data so that you can access it immediately, right? Symbol tables in compilers, you can use it to map variable names to their memory locations, right? Yeah, so in your compilers and interpreters, right, under the hood they use hash maps to hash the keywords, right? So you use the hash maps to map the keywords and their particular, or you can just map keywords and identifiers in any way you want to use to design the underlying infrastructure, the underlying algorithm for your interpreter or compiler. Then we use hash map. We use index applications of hash maps also involve using databases, right, for indexing. So I don't know if you heard anyone say, oh, just if you have, if your database performance is slow, right, just index it. So what does indexing means? Indexing essentially means grouping by a particular column on your database, right? So um you can index rows based on values in the columns, right? Let's say you have your database comprised of ID, you're storing the ID, name, email, and password, right? You hear people say, oh, your database is slow, just index it now and it will start working fine. Right? What they mean basically is you can index by ID, you can index by name, index by email or password. So essentially what it does is it to create yeah, to create an index. That's what the name is, right? To create an index where it stores um rules, right? It will store the, let's say you have 1000 rules in your database, so it will store them based on a particular key, right? And we know that emails are, you can't have duplicate emails in your database, right? So what it do is it will index everything according to the email. So instead of you looping through, because when you do select whatever, it will have to loop through everything and kind of get that particular value that you're trying to search for. But when you index it, it's kind of doing a get operation on the database, on the database, which is way faster than having to scan through all the records in your database. And yeah, there are also the underlying implementations for sets as well, which you'll see in the upcoming days. And yeah, they're also used in web development for session management and routing. If you've heard of cookies or sessions, yeah, the underlying implementations are just hash maps. Right. So and if you have any questions, please you can ask now if there's anything you don't really understand about the implementations, or maybe you missed something on the buckets array or how to handle collision. You can let me know before we move forward. Okay. So I'd like us to move into writing a custom hash map. Not the best, this won't be the best hash map, right? But I tried doing it before. So let me just this. Yeah. So let's get started writing our custom hash map. So for this, I'll introduce a new data structure, right? Linked list. I think to help us to kill two birds with one stone, right? It's where we just touch the two data structures effectively, right? Linked list and a hash map all in one. I think that's what I like most about this. And yeah, this won't be the best implementation of the hash map, right? But I think you still learn more if you like try to do yourself, right? It won't be up to the standard of when we are calling a dictionary in Python, because those guys have actually put in the work for it to make our lives easier. But I think we'll learn to appreciate it when we write it from scratch. So yeah, so the for this, oh, I would like to use yeah, like I said, the linked list, right, for the buckets mainly to store the information. So we have a node called, so the node is essentially what we hold our key values, right, in our hash map. Let's see, it's let's see, key, let's see, is equals say values, say next, the next node, right? So self key, six, yeah, supposed to. If you have any questions, please do let me know so can tackle this. This must be next node. So let's see class hash map. Um, definite self set the size of the hash map. So let's define the default size for a hash map. So the size um, size self the capacity is equals to node. So what this capacity essentially means is that in we will define an array, right? An array of nodes, right, containing this particular size. So anytime we define a hash map by default, our hash map will have 10 spaces, right, and will contain 10 empty nodes, right? So one moment, please. Just, okay. So let's define the hash function here. So let's see hash function there. So it's you can write a hash function any way you want to write it. But for this, I have a preferred method, or what I learned online was you can multiply the values, or like the ASCII characters of the keys in the ASCII characters of the elements in your keys, right, with a prime number to kind of increase the variance. So you don't necessarily always land on the same um index. It helps you to reduce the amount of collisions you have. So let's see for value in keys hash value multiplied by prime number. So it's the one plus odd. So what all does is it just converts the value to it converts that particular character to its ASCII value. Then like here's return size. Okay, so it should be a private function. So yeah, so I'm making hash a private function because it will only be accessed within the important functions as get, insert, and delete. So yeah, now we have the basis to work on our get function. Let's just say self. So what we want to achieve basically is we see map get key, right? We want to have our key here. Okay. Index plus hash indexing the key. We want to see the node particular cell, the capacity index. So this will give us the node at that particular index, right? So we want to check if node the value is none. That means it's nothing at that node, right? Just want to print there is value. Let's see. Right, so I just want to return. I also want to return is okay. So if there's a new okay, so what this handles now is if there's no value at that particular node, right? So I just want to tell ourselves okay, there's no value at that particular node, I want to return, right? But yeah, remember I said this is a linked list, and yeah, we can. What if there's a case where there's a collision and yeah, what if there's a collision? So we want to actually check the beginning of that node up until we want to keep checking throughout the sequence of the linked list until we get our actual key, right? So we'll just iterate through the linked list as well. So while node is not none, okay, node is not none. I'll say if node dot key equals key. So this prints node of value. Alright. If not, someone says node the next. Alright, so what did Those essentially is, let's say we have um at this particular node, right? Let's say we have nodes connected to each other at this particular index, right? What we want to check is this particular key value, key value, key, key. So what I want to check essentially is while the node, yeah, so we know that we are at this index, right? And we've checked, oh, if this node, if this particular node's value is none, right? So we know that there is not another index. But if not, we know that is something, right? And we want to check that while this particular node is not none, essentially, or we can say, okay, while node of value, let me change it so that we understand it right. While node of value is not none, right? Because anywhere, effectively, the idea is anywhere we insert a key, we should have a value, right? So let's check the value instead. While the value is not none. So while it is not none, because the default here says that value for like an empty node, right? The value is always none. Right. So um let's check. Let's check node. I'll explain why it is node. Right. So while this particular node is not none, right? So yeah. Yeah. So while this node is not none, what we want to check is the key value. So let's say at this particular index, oh, this particular node, or at this particular index, right, we have a key value. Then we'll check, oh, is this, if this key, if this node's key is not equals to, if this node's key is equals to yeah, if this node's key is equals to the key we want to get, we just print it, then we return. Right. If not, we update the node to the node dot next, right? Because we know that dot next will next points to the pointer to the next node, right? E- Essentially updating this particular node value. So we go again, we check this node. Oh, if node dot key is equals to this, print it and return. Or if it is not, it keeps going, it keeps going. And if we get to a point where it is equals to, we print it out and then we return. If not, we keep going, right? And if we don't see any key there, it will just effectively return false. And yeah, but the idea is that I doubt it will ever reach this case, because if yeah, if the node is not actually there, like if the value, if the value of the key we want to get is not actually there, I don't think if it's not the first index, right? And if it is not, if it's not the first index, surely it should be within the linked list, right? So that's the idea. Yeah, do it someone else. Please let me know if you have any questions. So um do, let's see, it gets string sorts. Right, so say self key. So let's compute the index self the hash key. Yeah, let's see node is equals to. Oh, okay. So we want to check node, right? So capacity square index. Um yeah, so we have the node. So we want to check if node of value if node of value is none. Um, so we want to see, okay, when, let's say, yeah, we want to check. So when we want to insert, right, we want to do two things. Want to check, oh, is that value, is the node, no, because we've already initialized n number of nodes, right? So at that particular index, we want to check this node, is it empty, right? If the node is empty, what we want to do is just update it. So just say node the key is equals to key, node the value is equals to value, right? Oh, so the insert should be key value. Yeah, right. So if not, like, oh, let's say there's a value there in case of collisions. How do we handle collisions? We want to loop through the end. We want to loop till we get to the end of that linked list, right? Then add our particular node, right? We want to loop through the end of the linked list, create a new node, then add it. So let's see, well, this, let's see, node is equals to node next, right? Right, is right. Well, node next. Want to update node. Right, up until the point where there is no node next. So node next. First, create a new node. Then the key value. Right. Mm, okay. So what we do now is, okay, let's say there's a value, right? There's a value at that particular index. Right. So what we want to do is, since we have our buckets as linked lists, we want to iterate through the existing chain of linked lists at that particular index. And then when we get to the end of the linked list, we just create a new node, then add it. Right. That's what we want to do essentially. Um, it's uh, let's see. Def deletes. This is key. Um, see, let's complete the index as well. So let's see if node value is not none. What I want to do is oh, okay. Let's say if node value, I want to check if the keys are the same. If node key is equals to key, I want to do is say node value equals to none, and the key is equals to none. Right. So if not, let's see. Node next. Let's see. Node key. Let's see. Customer. Zero, five, none. Right. Um, yeah, I guess that's it. Then so, move on next. Next. Okay. So yeah, I think so for the delete function, right? So what we do is we compute the index of the key we want to delete. Get the particular index um in the capacity uh get the particular index in the capacity list. Then we do what? Right. Then we reset it to none. Right. We reset this particular values to none. So what we do is we get the index, we get the node at that particular index. Then if they are the same, right, we just set it to none. This is in the case where we have only one value. Then in the case where we don't have, the case where we're on that index, right? Computed the index and it is not the first value, so it is within that chain of linked list, right? Uh, we just have to loop through the linked list. Then where we see the key, we just set it to none at that particular point. Right. So yeah, I think that works. So let me see. Custom. Let me see. Hash map is equals to hash map. Let's see. Hash map to insert. Let's insert two things. Josh. So what we do not get to keep printing. So let's say hash get name. Right. So let's run this. Let's see if it works. Okay. So you said that when we do hash map dot get name, we get Josh as the value because here we inserted name, we inserted the key name and the value as Josh. But if we try to get something that doesn't exist, let's say school. All right. Oh, this should try an error. Let's do this instead. It says no education node. Next node has not shipped. Oh, next. Okay, next node. Can we do this? Next. Okay. Let's run this. Okay. Let's see. And the gets do this. If it's not, let's print the. This is the index. Okay. So sorry, this is a bit smooth debugging. Alright, so let's do please how I able to highlight all the next. Oh, I did control D. Control D. That's how I highlighted all the next. So let me see. Node index of index and key, right? So this is index 8, right? So if not, okay, can I change this? If not node, do this instead. I get it. Says so I want to check if node of value. By default, this should be none. So let me see friends here. Oh, that's strange. Okay, I'm going let me select here. Oh, okay. I took a different approach, but let me see if I can write this. So let's say while node, right? While node is not. So if node the key is equals to key, so we just print key here, new value. Then I'll say node is equals to node next node x. So so let's do here is print the key does not exist. I can return. I'm saying it should work. Yeah. So this makes sense. The key name does not exist. That's possible now. If I think this already. So yeah, Ahmad can talk.
Okay. I think firstly the key name it exists, and the key name is it still prints the key name does not exist. I think perhaps
Oh,
the
I
print
think it's a
statement
return
can help.
value.
Yeah.
Oh, so this doesn't break out, right? Okay. So it should work now. So when it prints it, it should, yeah. Okay, this works now. So let me remove this guy. Yeah. So this is, I mean, like, I want to say we've built our own custom hash map. I want to see, but like, you can't use this in production, never. Like, there are a lot of things that are missing here, right? So here, kind of changing the node values to none. Like, how do I actually balance the linked list, right? So let's say I find the key in the middle of the linked list, right? I'm just setting everything here to none, right? Ideally, I'm meant to reshuffle, or should I say rearrange the linked list properly. But I don't think that's the aim of this class, right? I mean, we'll be able to write a hash function that works for us. So I can do hash map. So this I get. So I can this is an invalid guess. Let me remove it. So let me see if I can do hash map to remove. Okay, but delete. So let's delete name. So I just want to print. How am I doing print f? deleted. So F deleted key. So say key from no. Let's see if we see it. There's the turn. So next. So what the return statement essentially does is just, since we've already done the operation, just return instead of, because if the return statement is not here to still run through the whole code, right? So let's try the delete method. Let's see. So yeah, it says deleted key name from our hash map. So if we try to do hash map that gets name now, should get an error that doesn't exist. Yeah, so you see the key name doesn't exist. So essentially this is a very, very, very basic hash map that we built from scratch using linked lists, right, as the buckets. So I think this class we've successfully looked at what a hash map is, how to, like, what a hash map is, the underlying hash function, how to handle what a collision is, how to handle a collision, different methods of handling a collision, real world applications of hash maps, and we built our own mini-sized custom hash maps. So please, if you have any question, do let me know so we can go over it together, either code wise or whichever way. If you don't understand anything properly, so you can go over it and kind of discuss. Okay, yeah, Ahmad, please ask your question.
Okay, thank you very much. I really appreciate that. Can you explain to us again, like how the collision is handled in HashMap?
How
Collision, the collision is
collision? Oh,
handled.
okay, okay, with code, right? Should
Yeah,
I explain with
yes.
code? Okay. Um, I think the best way is to no, I'm not sure. Let me see. Two values that nice. I can't. Okay, so let me insert something here. Let me do hash map dot insert. I actually doubt. So let's see. I can't add name because that key already exists. Because mm, okay, I'm not actually checking if the key exists here, right? Okay, okay. So I'm not actually checking if the key exists here. So I can do hash map. Let me see. Name again as James. Right. So let me not delete this. Let's see if I get this, what will happen. Okay. Yeah, I get Josh. Okay. Let me see if there's a difference. Okay, so let's just, yeah, it's a print Josh. So if I do, let me do all gets. Right. So the all gets. So this will be a different method because if you check here, I'm not really checking against, oh, if yeah, I'm not really okay. Where's the insert? Okay, yes, yeah, I'm not strictly telling the hash map that if the key already exists, don't add it, right? So here, that's why I can add like same keys. But I'll use this explanation to kind of explain what collisions are. So ideally, this shouldn't be possible, right? If you use Python and any other programming language you use, you can't really add two keys, like two values with the same keys, right? But let's use that way as an explanation to handle collisions, because these two values now, yeah, they will give me the same index, right? And if in our inserts here, right, we are checking to see, okay, if the value is non-known, we add it. But if there's a value there, we want to go to the end, then append it, right? So let me show you how. Let me print out all the nodes in a particular what are they calling it, in a particular index. So let me define a new function called all get, so we can see it key. So what this does is one node is not known, so it will just keep doing this, right? Print key uh, key node the key as value this. Okay, let me not return here. Right, so let me do all gets instead of gets. So hash map the all gets name. So let's see. So exactly. So we can see now that when we first did get, okay, let me print something so we can see the differentiator. Right. So when we did the gets, right, when we did just get name, we're getting the first value, the value of the first node in that particular linked list at that particular index, right? But since we have two keys that have the same, that potentially results to the same hash index, you see that we added it, right? The thing added, and when we printed all the nodes with this all gets, when we printed all the nodes at that particular index, so it gave us key name has value Josh, key name has value James, right? So in the event where this is not possible, right? Ideally, we shouldn't be able to have name. Let's say we have something like fruits and apple, right? Let's say we have fruits and apple. What this will do is okay, this is already a collision, right? Name Josh and name James, because these two keys give us the same index. This is already a collision. And how does it handle it? What it will do is it will, when it gets to the end of the link, what this does is effectively iterating through the linked list at that particular node, right? So when it gets to the end, it will just add a new node with the key values. So what all gets is doing is just printing all the linked list, right, in that particular node for this key. So in the events where we have two different keys that result to the same index, right, what it's going to do is it's going to check, okay, and at a particular node, right, while the node is not known and the key is equals to key, to just print it and then it will return. If not, it will keep iterating through the list, right? It's keep iterating through the list, through the linked list. And if this is I'm at the end, oh, there's nothing I can do at this point. It's just print the key doesn't exist, right? That's what it just does. Do you get? So that's the point of collision. I hope this could answer your question, Ahmad. Did he answer your question?
Uh, somehow, but what of how do we handle it to avoid like, or for example, how it is done in some languages, say by the second value override. So,
Oh, so in this case, it doesn't override, right? It doesn't override. So, like I explained before, right? A linked list. So what the linked list does, it doesn't necessarily override it. It just changes everything together. Do you get?
yes.
Yeah, it doesn't override. So I can still print um so if I want, I can print only James. If I want, I can print only Josh, right? It doesn't override. Instead, what it does is like it changes both of them together. Do you get?
Yeah.
Yeah, so that's what this next node is doing. So essentially what I'm doing here is that, okay, since I've gotten the node at this particular index, Abby, so I want to iterate up onto the points where that node is none. Do you get?
Mm,
So
yes.
what this does is, okay, while the node is not none, that's while I have something in that node, right? I now
Mm,
want to check, oh, is the key equal to this key that I'm trying to get,
mm,
right? Then if the key is equal to the key, I just be, okay, yeah, the key this has the value this. That's why I can see two times. It didn't override it. What I just did was go. I when I did insert twice, then in that particular node, in that particular index, let me remove this. So what I did was, when I inserted name twice, okay, if I insert name again, you see I'm not overriding. You see, if I insert name, Mike, if I print it, I should have three names there. You see, I'm not overriding it. Do you
mm,
get? So what this does essentially is, at that index, right? What I have is an object that contains name and Josh, then a pointer, okay, to the next index, to the next linked list. Then the next one, I have name, I have James, and I have another pointer pointing to the next linked list. Then finally I have name, then I have Mike, then I have a pointer pointing to another linked list. But this one now, since it's not pointing to anything, it's pointing to none. Do you get?
yeah. Yes.
Yeah,
I think it's
exactly.
clear.
That's why, yes, that's why I can print all of them together. I hope it clears the issue now. That is not
Yes. Yeah. Thank
overriding.
you.
Yeah.
Yes.
So, but
So
ideally, ideally, this shouldn't even be possible, right? Ideally, this shouldn't be possible. So if I was to do it, I'll come to this insert, right? And I'll say, oh, if node key is equals to key, I want to check. I just print here that, oh, this key already exists, and I return. So if I try to do it now, I should have error. Can you see this key already exists? This key already exists.
yeah.
Then the only thing to now print out is Josh. Can you see?
Mm, yeah.
So yeah, that's just how it is.
Okay. Thank you very much. It's clear.
Yeah, yeah, you're welcome. You're welcome. Please, if anyone else has a question, please just let me know. Yeah, David, your question.
Please, can I just get an over, because you were creating a diagram using linked list to explain hash maps. Can I just get
Yeah.
an Yes? Can I just get an overview of each function and how it relates? Like,
Oh,
function,
okay.
delete of the hash map.
Oh,
The hash map.
okay. Yeah, so what okay, so first we have like the node, right? This is the building blocks of the individual components of what we have in our hash map, right? Then we have the hash function. What the hash function essentially does is computes a value, a hash value, right? That when we apply a modulo to the size of this particular hash map that we want to have, right? So what this value will do is, what this modulo does is it just makes this value be in the range of this particular size. So if I have 31 and I do 31 modulo 10, my value, my answer, right, will be in range of 1 to 10, no matter what. If I do 10 modulo 10, my answer will be in range of 1 to 10. If I do 1 million modulo 10, my answer will be in range of 0 to 10, right? So this is what we use to get the index of where we should store the value, or where we should store the particular key value pair we want to store in our hash map, right? So when we do get, what does get mean? Essentially, what we are doing is that, oh, this get function, we want to, when we use get, we want to give it a key, right? And we want to retrieve the value of that corresponding key. So what we do is we compute the index of that key. Then we know, since we know that our hash map, the list of our hash map essentially contains a list of nodes, right? We mentioned that we are using the linked list to handle collisions, right? In the case whereby um two different keys may essentially map to the same index, right? So what we do is, if they map to the same index, we are using a collision technique called separate chaining. And what separate chaining does is involves the use of linked list, right? Where instead of let's say the map to the same index, we just append the new node to the back of the existing node, right? So instead of like adding adding that collision key value to a new index, we add it to that same index but append it to the end of the linked list. Do you understand? Yeah, so that's what it does. So what we now do here is that, okay, when we are doing get, we want to essentially loop through all the linked lists that we have. That's if we have, like, worst case scenario is that we have like a long chain there, right? And want to loop through everything and get the particular key that matches the one, and get the particular node that matches with the key that we are searching, and return the value. You understand? So let's say in this index now we have only one node, right, and his name, and it maps to my Josh, right? So what we want to do is we want to loop through the linked list up onto the point where it is pointing to where it's pointing to none, right? And we know that when it's pointing to none, we've gotten to the end of the linked list, because we defined here that all our linked lists, the next node should always be pointing to none, except we update it, right? So the idea is I want to loop through the linked list up onto the point where it is none. Then while looping, we want to check, okay, for each node, we want to check, yeah, is the key of this particular node equals to the key that we want to get the value for. And if so, just print it and then return. If not, update node to the next node. Do you get? If not, update node to the next node. That's why in the case of this James, Josh, and Mike, right, we could insert all of them, because our hash map didn't have a constraint whereby we can't have the same value. So we inserted all of them into the same index, because name will always compute the same index. But when we are inserting, we need to remember that we're handling collisions. That's what the linked list was for. So when we inserted Josh, then we inserted James immediately after Josh, then we inserted Mike immediately after Josh. So when we print that's so when we print this, right? If we remove that check, if we remove this inside, if we remove this check here and print this, you see that we have Josh, James, and Mike. Yes, this is an issue. I remember Josh done. So yeah, you see that we have. Let me even remove this long. What is that thing? This long stuff. Let's print it very big. Now we do all gets essentially look through the linked list, right, and print the values Josh, James, and Mike for the particular key because we're trying to get all the values that associates with the key name. That's what all gets means. But get will only give us the first value that it encounters that is equal to that name. So if we have fruits, right? If we have fruits and we have apple, and we have wrestler, I'm say wrestler, and we have the rock. Hypothetically speaking, right? Hypothetically speaking, that name, fruits, and wrestler give us the same index. When we do insert, this is what we are going to have. And when we insert name, fruits, and wrestler, this is wrestler. This is this fruits. I mean apple. This is the rock. Right. So hypothetically speaking, let's say these three values map to the same index. This is what we are going to have in that particular index, right? We have a linked list of name pointing to fruits, pointing to wrestler. Do you understand? So anytime we do the get now, since we are doing the get on a unique key, it will first check the first node of that index. Say, oh, his name equals to name. Yes, okay, to just print out Josh for us. But if we do wrestler, it will check his name equals to where's that place get? It will check if node or key is equals to key. So it's check if node or key. The first one has to be name, right? That will be the first key. Key is not equals to wrestler, it will not go. It will update node is equals to next node. It will move to fruits. It will check if fruit is equals to key, fruit is equals to wrestler is not. It will go node is equals to next node. Then node is equals to wrestler. Then it will now check if wrestler is equals to wrestler. It will print to say I've gotten wrestler. Then it will return. That's essentially what it does. In the case whereby name, fruits, and wrestler all map to the same index, right? So that's what the get does. It gets a particular key. If it is unique, it will get that particular key's index. That particular key's value rather. So all gets, like I said earlier, what all get does is it will look through all the linked lists of that particular index and print out the values. Then what insert does is insert computes the index, right? It computes the index of a particular node, right? Then it checks, oh, if this node value is none, essentially, if that node is none, there's nothing there, just update the key and the value for me. That's all. If not, if there's something there, right, loop through to the end of that linked list, right? Loop through to the end of that linked list. When you get to the end, just update it for me and just update that end, right, with the key and value. That's actually what we are doing here before with name as James and name and Mike, right? So what it did was, okay, if node or value is none, let's say we add insert Josh, I'll be the first one. So it's check node or value is none, of course. The first insert is none, so it's update key value. Then to do insert again James, okay, at the same index, it will check if node or value is none I can say that node of value is not none. I mean, there's something there. It's not okay. If there's something there, check while node dot next. That's while there's something. That's like while the next pointer is pointing to a node, right? Just update it for me. Do you get? While node dot next is like while node dot next is not none essentially. That's what this statement is. While node dot next is not none, just update node to node dot next. Do you get? So while it will now check, okay, name the first index, that particular index that is name. It's a check name. Oh, it's first check, okay, value, there's something there. Then it's now check node dot next. Okay, then this one now, node dot next is none. That's for since we have nothing yet, right? Node dot next is none. I'll be pointing to none. Then when you want to insert James to check, okay, node of value is there's something there. Then while node dot next, so it's okay. I'm on node dot next is none. Then it's update node dot next for me to key and value. And by default, this new node that it is updating, the next node is none. Do you understand? So like that now, we have this. Let me do this. Let me do this. Let me do it. Yeah. James, no, yeah, James. Let me cut this. So like that now, what we have is in the linked list now, that particular index is name. We have name, where name is Josh, where name is James, and we have the last one now pointing to none. You get? So when we now do insert again, Mike, what you to do is that at that particular index, know that there's something in the first node of the linked list, Abby. So we want to check, look through the end of that particular linked list at that index. Okay, while node dot next, while there's something, like while the next node is not empty, update node for me, right? And keep iterating. So to check, okay, Josh's next node is not none, right? That means there's something there, Abby. Then to update it to James. Then James' next node is none. Then it now creates a new node there for me. Then if we do this, let me change it to, we'll now have name and Mike. The Mike will be pointing to none. That's why if we print it out, if we print out get all, since they have the same index, since they have the same key, they should map to the same index. But you see how it is not rewriting it. It is just updating the next node value for us. So that's insert. That's what insert basically does. Then what delete does essentially is it will look through that key now. What it does is okay, that key, what it does is it will loop, it will get to the node, right? Then if it says that okay, node dot key is equals to key, just set it to none, and it will tell us, oh, I've deleted all the keys that have this name in our hash map, right? Then if the in a case whereby we don't have the same name, or let's say in a case whereby the key is not the first value in the linked list of that particular index, it will keep looping through the linked list, right? And to keep checking. Then until it says, oh, okay, I've seen the node where the key is equals to the key that I want to delete. So just update it. I say node of key is equals to none, node of value is equals to none. Then return. If not, it will update it and keep iterating. So that's just it. Those are what the functions does essentially. So yeah, I hope that answers your question, David. Oh, he's not here. But please, if you have any questions, do let me know. Hazan, Elizabeth, Ahmad, if you have any questions, please do let me know. Okay.
Thank you. I don't have any question. Thank you very much.
Oh, okay. You're welcome. You're welcome. So I guess we are almost. I think we are at the end now. Yes. Thank you very much, everyone, for coming today. Tomorrow we'll go through. Oh, I think someone's raising up their hand. Okay.
So, sorry, I wanted to quickly ask, like, which resources, like, did you recommend for us to learn this DSA well?
Okay, which resources should I recommend?
Yeah,
Oh, okay. I highly recommend getting started, right? I recommend Neat Code. Okay, let me go. Let me show you guys. Can you see my screen?
yes,
So can you see Neat Code, right? Neat Code, the better it's prepared for coding interviews. He has a free roadmap. Okay, let me see practice. So you can see you can practice by data structures. And he has it outlined in such a way where it's very, very easy to learn. Why is it not updating? So, okay, this is design. Uh-huh. So I mean, if you sign in, you see a lot more. But yeah, he has different. He has well structured. So you can, yeah, even has courses, algorithms, and data structures for beginners, advanced algorithms. But I think all these ones are paid, sha. But yeah, it's still you can just this is like the best place I recommend beginners to come through because um he has detailed should I say roadmap, detailed roadmap that help. So just come here, you get started, just sign in that you can get the questions and you can start from arrays, 2 pointers, stacks, binary stars, sliding windows, linked lists. Yeah. Then when you are
sorry,
done with them, yeah.
okay, sorry, I noticed it seems you have access to the pro, right?
I don't have access to Pro. Yeah, Pro
Okay,
is expensive. Pro is
okay,
expensive.
thank,
So I don't have
okay,
access, but I can send the website to the chats.
I've
So
checked
that.
it out before, but when I saw that pro, like the,
Oh no 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 no. Okay, let me sign into my own account. Let me show you guys. Um, let me show you. Um, so I definitely do have access to Pro, but I think the questions I've solved now. He has a list of questions. That's Pro. So I don't have Pro, but I have questions that I've solved. I know that I've solved some of these questions. That I can't get it or what? Oh, that's strange. I don't think I can access it anymore. But now I've solved a lot of these questions before. So yeah, but it's a great place to get started, right? It's a great place to get started. So yeah, he has neat code 150. Okay, I think this is the place. Why is it not showing now? Neat code 150. This. Yeah, this is it. So this is the question. So you see, he has array and hash maps. So you just click on it. It's meant to show you the questions. Exactly. So these ones I mentioned that See, he has 9 of this. See, arrays, hashing, 2-pointer, sliding window, stacks, binary search, linked list, trees. Yeah, you just see that, choose the one you want to do, then you decide whichever way you want to do it. So yeah, that's neat code. Then after neat code, I advise start solving elite code problems. Then if you are looking into applying for internships, just yeah, you can just start looking into company-based questions. Well, we had a webinar for that recently. If you want, where we had industry experts walk us through how to like get started with elite code for landing internships abroad. So yeah. So
Thank you very much.
yeah, very much welcome.
You mentioned another one, getting started.
No, it just needs code and leads code and needs code. Those are the only two.
Okay.
Yeah.
Okay. Thank you. Thank you very much.
Yeah. It's just you that needs to, put in the work. In as much as everybody mentions these sites, it's just you that needs to sit down and actually solve those questions. So yeah. So thank you very much, everyone, for attending this class. I really appreciate it. Yeah. So thank you, everyone. Have a good evening and stay blessed. Okay.